You probably remember the noble gases from chemistry class. They were those stable, predictable, and, let's be honest, kind of boring elements, right? The ones sitting in their own quiet corner of the periodic table. But what if that whole nobility thing was just a cover story? Seriously, what if these supposedly standoffish, unreactive elements were actually hiding a pretty explosive secret? Well, it turns out they are. And their story is just this fantastic lesson in how even the most settled science can be flipped completely upside down. All right, so first up, let's meet the family. You'll find them tucked away in Group 18 of the periodic table. For the longest time, everyone saw them as the aloof aristocrats of the elemental world. They just didn't mix with the common folk. So who are we talking about? Helium, neon, argon, krypton, xenon, and radon. They got that noble name for a very specific reason. Their outer electron shells are completely full. Now, in the world of chemistry, a full shell means you're stable. You don't need to borrow, you don't need to lend, you don't need to share electrons with anybody. You are chemically self-sufficient.
This chemical snobbishness leads to some really bizarre physical properties. Because the atoms don't really interact with each other, the only thing holding them together are these super weak, fleeting attractions called London dispersion forces. The result? Shockingly low melting and boiling points. I mean, helium is the ultimate example. It literally refuses to freeze at normal pressure, even if you cool it down to a tiny fraction of a degree above absolute zero.
So, for decades, this idea of them being totally non-reactive was just scientific dogma. It was fact. But then came a huge upset. A single experiment that was about to challenge everything chemists thought they knew about this so-called noble family. For ages, their inertness was just a fundamental truth. Then, in 1962, a chemist named Dr. Neil Bartlett did the unthinkable. He actually managed to create the very first chemical compound using a noble gas. He proved that long-held assumption was completely, totally false. And look, this wasn't just some small correction in a textbook. This was a revolution. Before 1962, you'd be told it was impossible. After 1962, a whole new field of chemistry, totally dedicated to noble gas compounds, just sprang into existence, all because of one groundbreaking discovery. But here's the really interesting twist. Just because they can react doesn't mean they're not still incredibly stable. In fact, it's the general unwillingness of the lighter noble gases to get involved that makes them so unbelievably useful to us. Just think about helium. We feel party balloons with it because, unlike hydrogen, it won't burst into flames. Deep-sea divers breathe a mix of helium and oxygen to avoid the dangerous effects of nitrogen under pressure, called the bends. And in really high-tech applications like welding, or even inside an old-school light bulb, helium and argon create this protective, non-reactive bubble that stops other elements from messing things up.
The stability is also absolutely crucial in the world of the super cold. Now, liquid nitrogen is a pretty common coolant, but sometimes it's just not cold enough. And that's where liquid helium comes in. At a mind-boggling minus 269 degrees Celsius, it is essential for cooling the incredibly powerful superconducting magnets you find in MRI machines. The things that make modern medicine possible.
And of course, we can't forget neon. You pass an electric current through it, and its electrons get all excited. When they fall back to their normal state, they release that energy as that brilliant, iconic red light we all know. Its stability is the reason a neon sign can just keep on glowing for years and years without degrading.
Okay, so the lighter gases are useful because they're stable. But what about the heavier ones? This is where things get really interesting. This is where we meet the reactive rebels of the family, the ones that proved Neil Bartlett was right all along. So how in the world do you get a noble gas to react? Well, it's not easy, but you can do it. For xenon, you basically take one of the most reactive elements there is, fluorine, mix them together, add some heat to get things going, and as you cool it all down, you get something amazing. These stable, colorless crystals of a noble gas compound. But right here is where the story takes a truly shocking turn. You take one of these new xenon compounds, you react it with plain old water, and you create something called xenon trioxide. Now, this solid isn't just reactive. It's a powerful, highly unstable explosive that can detonate completely spontaneously. Yeah, so much for being noble. And xenon isn't alone in this. Krypton can be coaxed into forming some pretty unstable compounds too, and even radioactive radon has been shown to react. So you start to see a clear pattern here. The farther down you go in the group, the bigger the atoms get, and their outermost electrons are just further away from the nucleus, which makes them way more easily lured into a chemical reaction. So, where does that leave us?
We've gone from party balloons to powerful explosives, all within the exact same family of elements. It's kind of crazy. It's time to try and make sense of this fascinating dual identity.
It really is like a tale of two families rolled into one. On one side, you've got the aloof protectors, helium, neon, and argon. Their stability is their superpower. It's what makes them useful. On the other side, you've got the hidden rebels, krypton, xenon, and radon, whose reactivity unlocks this whole other world of powerful and sometimes dangerous chemistry.
So, what's the bottom line here? Well, first, we've learned the name noble gas is, a bit of a lie. Second, while their relative stability is incredibly useful, it's their hidden reactivity that opened up entirely new fields of science. And maybe most importantly, it's just a powerful story about how a single discovery can completely rewrite the textbooks.
The story of the noble gases is just such a great reminder that what we think we know in science is never truly set in stone. It really makes you wonder, what other settled science is just one discovery away from being completely upside down?